Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to continue our discussion about linearly independent versus linearly dependent sets of vectors. So in a previous video you saw that a set of vectors is linearly independent if the homogeneous vector equation has only the trivial solution. And we had a formal process for determining that. We created an augmented matrix using our vectors as the columns of the coefficient matrix, augmenting with 0. And then we did our row reduction to put it into REF form. And that way we could identify where the pivots were. We could identify where the pivots would be in the coefficient matrix A. And the idea was if there was a pivot in every column of A, well, this meant that there were no free variables. No free variables meant there was only one solution to the homogeneous equation, and that meant linearly independent set of vectors. And that was our workflow, kind of our formal process to determine whether the set of vectors was linearly independent. But a set of vectors is either independent or dependent, and sometimes it's actually easier, there's shortcuts to determine when a set is linearly dependent based on the characterization of linearly dependence. So let's take a look at that. So we have this theorem that says a set of vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the other vectors. And so this characterization helps us determine whether a set of vectors is linearly independent or dependent. If we recognize that one of them is just a linear combination of the others, we can jump right to the conclusion that the set is linearly dependent. So why is this true? Well, we have an if and only if statement. This says our theorem kind of points in two directions. If the first thing is true, then the second thing is true. And if the second thing is true, then the first thing is true. So to talk about this, I want to really describe both cases here. So the first thing says that if our vectors are linearly dependent. Well, what does that mean? Well, that means there is some non-zero solution to the homogeneous vector equation. So I'm going to make up one of those solutions. That basically means that if I have three vectors in my set, that there's some non-zero set of solutions. Maybe it looks like this. I'm going to put a pretend case of solutions here. Maybe there's some solution that looks like that. Well, if that's the case, then what I could always do is solve for one of the variables. So I could say, well, then 2v1 is equal to minus 3v2 plus 6v3. And then I could just multiply through by a half to get negative 3 halves v2 plus 3v3. And this way I've written v1 as a linear combination of the other two vectors. So now we can see that thus v1 is a linear combination of the vectors v2 and v3. Now obviously this isn't a proof, I just use a specific case, but we can generalize this and say that if this was any number of vectors and these were any non-zero constants, you'd still be able to solve for one of those vectors. And in that way you'd be able to represent it as a linear combination of the other ones. Now what about the other direction? We say if v1, for instance, for example, picking out one case, is a linear combination of the other two vectors, v2 and v3, for example, well, then I should be able to write v1 as some number times v2 plus some number times v3, where x1 and x2 are both not 0. That's what it means for v1 to be a linear combination of those two vectors. But as soon as I can write that, I could just subtract the x1 v2 to the left-hand side and also the x2 v3 to the other side. And now I have a homogeneous vector equation where the coefficients are not all 0. So that's telling me I do have non-zero solutions. So thus I do have non-trivial solutions to the homogeneous vector equation, which implies the vectors are linearly dependent, which implies that the set of vectors is linearly dependent. Okay. Now once again, this is not a proof of this theorem, but it's the spirit of the theorem. And so you should really take this as an example and then look back at the proof from the text and see if you can line up kind of the generalization. But it basically tells us that if we look at a set of vectors and see that one of them is a linear combination of the other, then we can jump right to the conclusion that they are linearly dependent. All right, so let's see if we can actually use that theorem and apply it. All right, so here I have 4 sets of vectors, and I want to determine whether they're linearly independent or linearly dependent. So I look at the first one. Now I look at that first one, and just by recognition, I could see that I can build this third vector using the first 2 vectors. I can see that if I took 2 of that first vector plus 3 of that second vector, it would yield that third vector. So I can visually identify that one of them is a linear combination of the other 2. That immediately tells me that these are linearly dependent. I do not have to do an augmented matrix. I don't have to do row reduction because I can see that dependence. I know they're linearly dependent. So now I might look to the one to the right here. I might look to this set of vectors. Now I'm looking at those and I don't see clearly how one of them is a linear combination of the other. This is important that I cannot make the assumption that it's linearly independent. If I can see that one is a linear combination, I can state linearly dependence. If I can't see that one of them is a linear combination of the others, I don't know what's going on. So now I would have to form my augmented matrix. I would have to do my row reduction here. Okay? Because for all I know, maybe it's 1/7 of the first vector minus 4/3 of the next vector plus the square root of 2 times the last vector. Like, I don't know. So just because I can't see the linear combination doesn't mean it doesn't exist. So I would still have to go through the formal process here. Because sometimes it's hard to see if one vector is some sort of combination of the others. Now if we look to this third example down here, well, this is a little easier. Because if I'm talking about just 2 vectors, in that case, well, then it's easy for me to determine if one is a linear combination of the other. Because if you only have 2 vectors, a linear combination would be just multiples. So for 2 vectors, either they are multiples or they are not. If they are multiples, the set is dependent. If they're not multiples, it is independent. That is a shortcut when you have just 2 vectors. So here I can see those vectors are not multiples of each other. So right away I know they are linearly dependent. And then I look to my last case here. I have these 4 vectors. Now, when I have a 0 vector in my set, that tells me I automatically have a linearly dependent set. And there's a couple reasons that we could think about that. One, I can already see a linear that one of these is a linear combination of the other. For instance, if I take 0 of this one plus 0 of that one plus 0 of this one, I get the 0 vector. And that is one of my linear combinations. Now, another way we could think about this is we really could think about what would happen if we formed our augmented matrix. If we formed our augmented matrix, we would have one column that would already be all zeros. And so we would do the row reduction, but there's no way I could add a pivot to that column that started with all zeros. So without having to do the row reduction, I already know that at least one of the columns will not have a pivot, which means there will be free variables, which means there will be infinitely many solutions, which means the set of vectors is linearly dependent. So I kind of know that all as soon as I see the 0 vector in my set. So this is how we've applied that characterization of linearly dependence to quickly determine whether sets of vectors are linearly dependent. We have one more shortcut that we can look at. The last shortcut for determining if a set of vectors is linearly dependent is if we're given p, some number p of vectors that are in Rn, if p is greater than n, the set is linearly dependent. That looks kind of like an ugly statement, but let's see what it actually means here. If we consider this specific set of vectors, well, what we have here is we have 3, so we have p equals 3 vectors. So p is the number of vectors. And where do these vectors live? These vectors live in R2, right? So that n value is the number of components that are in our vectors, what space they live in. So according to our theorem, it would say that since 3 is greater than 2, the vectors are linearly dependent. But why is this? Why does this have to be? Once again, there's two ways we can justify this. We could say, well, if we were going through the more formal process, we would create our augmented matrix. We would augment with 0, and we would do our row reduction to REF. But because I only have 2 rows, I can only have at most 2 pivots because I only have 2 rows. But I have 3 columns in the coefficient matrix. So there's no way, so I can't possibly have a pivot in every column. So that tells me there's going to be a free variable. That tells me there's going to be infinitely many solutions. That tells me the set of vectors is linearly dependent. Okay, so if I have more columns than rows, that set has to be linearly dependent. Now, another way to think about that is in terms of span. So in this case, I'm looking at vectors that are in R2. I only need 2 linearly independent vectors to span R2. So in other words, if I take these first 2 vectors, I can look at them and tell that they are linearly independent. And so I know that I could create all of R2 just by using combinations of those 2 vectors. In other words, any vector in R2 I could build by taking linear combinations of those first 2 vectors. Well, if I can create any vector in R2, I could certainly create this vector in R2. And that tells me that this vector is really just a linear combination of the other 2, which tells me that the set of vectors is linearly dependent. Okay? So what we can see, if we have more columns than rows, the set is automatically linearly dependent. But be careful. We can't make the case the other way. If p is less than n, that doesn't necessarily imply that it's linearly independent. Okay? So if we have more rows than columns, for example, if I'm looking at this set of vectors here, like that, here we have more rows than columns, so we might be tempted to say, oh, this has to be linearly independent, but it doesn't. In this case, I can clearly see that those 2 vectors are multiples of each other, so they actually are linearly dependent still. If I have more columns than rows, I can't possibly have a pivot in every column. But if I have more rows than columns, I might have a pivot in every column, but I still might not. Right? So this doesn't tell me anything. All right, so that concludes this video on shortcut techniques to determining linearly independent or linearly dependent. Thank you.